Over the last couple of videos, we've talked about the skeleton outline of glycolysis. We've said you start with glucose, you make 2 pyruvates and 2 ATPs, and then in my last video, we went through step by step and looked at the 10 steps to get there. In this video, we're finally going to dig in and say, how in the world does that actually generate ATPs? So super cool, let's dig into it. So first, there's a lot of things that have to happen in glycolysis. I want you to imagine for a second that you have to push a heavy box. And think about, you walk up to the box and what do you have to do to move it? And what you might do if you start thinking about it is you realize, I really am bad at drawing people pushing boxes, that you have to line up and there's a bunch of moves that you do before you push the heavy box. Lots of steps set up this actual push. And then there's really like one step to do the pushing, right? And we see the same thing in glycolysis and actually a lot of metabolism where there's a bunch of steps that are basically setting things up to do something interesting at a specific step. And that's how we're going to think about glycolysis. The two interesting steps in glycolysis are at steps 6, 7, so right here, which is going to generate an ATP if we're running in this direction, right? So we're going to spit out an ATP. And then down here at the end, pyruvate kinase is also going to spit out an ATP. And what we're going to be asking is, how in the world does glycolysis do this? What's happening at step 6 and 7 and step 10 that allow a cell to make ATP? Cool, so let's just dig right into it. So I'm going to summarize these reactions really quickly again. What we have here is a glyceraldehyde 3-phosphate. We have an inorganic phosphate, and we have an NAD+. And we're going to see a couple of reactions here. We're going to see this hydride pop over here onto the NAD+, making NADH. And we're going to see the phosphate take its place on the 1 position of the glyceraldehyde, making 1,3-bisphosphoglycerate. We've also made an NADH. That's step 6. At step 7, what we're doing is we're now taking the 1,3-bisphosphoglycerate that we generated. We're taking an ADP, and then we're going to take that phosphate that we just stuck on, and we're going to stick it onto that, forming the ATP. So we've now basically gone from a G3P, glyceraldehyde 3-phosphate, to a 3PG, a 3-phosphoglycerate. Yes, annoying nomenclature. Sorry, it's the way that the world works. But what you might notice is we've gone from an aldehyde up here to a carboxylate here. So we've done a net oxidation of this carbon. And the other way we might know that is because we've had to reduce something, right? We've reduced an NAD+ to an NADH. So there was an oxidation reaction that happened while we were also doing a phosphorylation reaction. So what we're going to spend quite a bit of time here in a second is looking at this step. What's happening at this glyceraldehyde 3-phosphate step, which is both doing the reduction, the redox reaction, and the phosphorylation. So quick, just drawing one more time here. We're going to take the hydride off of the aldehyde. We're going to stick it onto the NAD+. We're going to stick the phosphate onto that position, yielding ultimately this 1,3-bisphosphoglycerate and this NADH here. And we have two sorts of chemistry happening, right? We've got a redox reaction happening, and we've got a phosphorylation reaction. How do we get both a redox reaction and a phosphorylation reaction? So first, let's look at these sub-reactions individually. Let's first ask, how favorable is it to oxidize G3P to G3P, glyceraldehyde 3-phosphate, to 3-phosphoglycerate using NAD+ to do the reduction? So if you want to think about how to set these problems up and do some practice, this is a great time to do so. So I will give you a second to pause and find a piece of paper and actually figure out what's the free energy for this oxidation. So pause. All right. Assuming you're coming back from your pause, let's go through this. To solve or to set up one of these reduction potential reactions, the first thing that we have to do is we have to balance the reaction. We have to do so by identifying what our acceptor is going to be and what our donor is going to be. So electrons flow uphill in redox reactions because that's the way the world works, unfortunately. But what that means is this standard state electron potential, this standard state reduction potential, there we go, has higher affinity or indicates higher affinity than this one because it is a more positive number. It is a higher magnitude positive number. And so what that means is this is our acceptor and this is our donor. That means that our products these here are going to be our reactants, and these here are going to be our products. So let's actually go to the trouble of writing all that out. So we're going to say that CH3CHO plus H2O, that is on the left. We're going to, and that's from this right here. I guess I'm going to draw boxes around them, all the way around them. And now let's use a different color for this side, right? So this is from the acceptor side. So it's going to get an NAD plus H plus 2E minus. Great. So we have flipped over the donor side and we've kept the acceptor side intact. And we'll use a different color here. We're going to write this one there. So this is CH3COOH plus 2H plus 2E minus. So that is there. And then we are combining that with, that is not the color I wanted. We can do this with an NAD plus, or NADH, sorry. So that gives us our NADH. Right, so we've set up the reaction. We can now ask if the reaction balances, and the way that we can do that is basically look for, can we cancel electrons? And in fact, we can cancel electrons on both sides. What that says is our N equals 2, right? We're moving 2 electrons in this redox reaction. If you look at our equation here, we have 3 terms. We've got our N, we've got our F, which is a constant, and we've got our delta E. So let's go calculate our delta E. The delta E is going to be the acceptor minus the donor, right? This is, our electrons are going to flow from the acceptor to the donor to the acceptor. So this is going to be the change in the standard state reduction potential, or the change in the affinity of the molecules for their electrons. That means you can plug in some numbers here. So if we plug in all of our numbers to this, we would get our delta G equals minus 2, right? We've got 2 electrons, that's our N, times our F, which is 95.49 kilojoules per mole per volt. There's a number that once you've taught this enough times, you'll remember. Otherwise, you'll just look it up on the internet. And then what is delta epsilon? It's going to be minus 0.320 volts minus 0.580 volts. As a quick check, we can check and make sure, look, our volts cancel, and we're left with kilojoules per mole. That's good. We want this to be an energy. And the final energy ends up being delta G naught prime equals minus 50 kilojoules per mole. So that's a lot, right? That is a lot of energy, saying it's going to give us 50 kilojoules per mole if we do this oxidation reaction. If we oxidize G3P to 3PG. Cool. So we can write that out here. This is now written out in more molecular form with the energy that the standard state reduction, or the standard state energy to do this, is minus 50 kilojoules per mole. What about the phosphorylation? It turns out the phosphorylation is super unfavorable. And the reason it's unfavorable is because if you think about this position, we have this phosphate, so it's big, bulky, negatively charged, decent leaving group, and it's in a carboxylate. So basically, it wants to fall off. This is a very favorable reaction to basically pull these negative charges off, let them do some resonance stabilization, because we can flip around through more resonance forms. So overall, this reaction strongly favors going in the dissociated form, and it does so by 49 kilojoules per mole. That means if you add up these two reactions, if you add up the favorable oxidation and the unfavorable phosphorylation, you get basically 0, right? Or minus 1 kilojoules per mole. So it's barely favorable to do this reaction. Overall, it's almost a 50-50 chance whether the reaction will flow backwards or forwards at standard state, but it's just barely favorable. So don't worry, we're going to make it all favorable by coupling it to the next step in the reaction. But for the moment, let's look at this barely favorable reaction and see how it occurs. So it turns out that the way that these we can do the favorable reaction and also the unfavorable reaction is by an enzyme that actually physically links these two reactions to each other. So glyceraldehyde 3-phosphate dehydrogenase is going to do both the oxidation and the phosphorylation all in one active site. And it's a cool enough mechanism and a good enough cool enough way to see how these works, I thought we'd actually go through it in a little bit of detail. So what I'm showing here is the enzyme. It's typically a tetramer. And so this is 4 different copies with different colors. And hopefully you can see down here, just peeking out in the middle, there's a little bit of stuff. That's our enzyme active site. So there's 4 active sites in these different subunits. We're going to zoom in and look at one of them, just the one in this gray one. So we're sort of rotating around so you can see how deeply buried this is. Hopefully you really appreciate that. This is deep inside a hydrophobic pocket, moved away from water, which enables the chemistry to happen without all kinds of interference from water. You'll notice that we've got a subset of residues labeled here. Those are the NAD plus is going to be in purple. The glyceraldehyde 3-phosphate is in green. Then we have an active site serine and an active site histidine that all participate in this chemistry. Let's see what happens in this active site. So what we have here is our active site serine. We have our glyceraldehyde 3-phosphate. This right here is that one aldehyde that's going to get reduced. And the way that this happens is you get a nucleophilic attack from the serine onto the aldehyde. That then grabs onto a proton from the serine, and you end up with this intermediate form. So you've covalently attached the glyceraldehyde 3-phosphate to the active site serine. I just moved the exact structure. So this is the structure here. I'm going to move it to the left. We move it over. Now we can talk about the chemistry that it's going to do. So what we're going to see then is this active lone pairs on this active site histidine are going to grab onto the proton from this X aldehyde. That is going to cause the electrons to flow to make the carbonyl, and then we're going to kick off the hydride, which is the electrons plus the electrons in the bond plus the proton. It's going to come up and attack here, and then resolve to this. So we've taken an NAD plus, and now we've converted it to an NADH by transferring over our hydride, which is our proton with 2 electrons. Okay, cool. Now, how do we couple that to phosphorylation? So this, event happens. The active site is going to, want to, resolve from this state. How does it do so? Well, a phosphate diffuses into the active site. So that sort of came in here. This is then followed by a nucleophilic attack from the phosphate and movement of an electron up here. This puts us into an oxyanion type intermediate. This then resolves by breaking this bond here, and I guess actually I should draw it like this, grabbing onto that proton, leaving us our active site restored, right? We've got our active site serine and active site histidine restored, but now we've done our reaction, right? We've got an NAD plus, and we've got our 1,3-BPG formed, right? So by physically putting all of these chemical moieties together and promoting a particular sort of interaction or set of reactions, rather than doing just say the favorable oxidation and not the phosphorylation, we do both the favorable oxidation and the unfavorable phosphorylation all in one active site. So we've done this just barely favorable reaction, making this molecule here, 1,3-bisphosphoglycerate. What happens next? Well, remember, it was super unfavorable to phosphorylate this, which means it's super favorable to dephosphorylate it, right? If we just chop off that phosphate, that gives us minus 49 kilojoules per mole. That is a super favorable reaction. If we just let this sit in a test tube for a long time, it'll happen. But instead of letting it happen spontaneously, we actually have an enzyme that's going to couple that dephosphorylation, which is minus 49 kilojoules per mole, to a phosphorylation of ADP, right? That's only 30 kilojoules per mole. So it's plus 30 kilojoules per mole to take a phosphate and stick it onto an ATP. And so we've got minus 49 kilojoules per mole driving dephosphorylation on the top. And we've got plus, I should make myself disappear for this one. And we've got plus 30 kilojoules per mole saying phosphorylate. If you add those up, it's still favorable to do the dephosphorylate, or to do this transfer. And it's favorable by 19 kilojoules per mole. This is catalyzed by the enzyme phosphoglycerate kinase. And so let's actually look into it. It's going to take this phosphate and stick it onto there, generating our ATP and our 3-PG. So how does that actually do this job? So basically what it does is it positions these molecules such that when the dephosphorylation happens, instead of the phosphate floating off into solvent, it's going to go pop and drop right onto an ADP. So in this structure, we have ADP here, and then this is our 1,3-BPG. And you'll notice those phosphates are like right next to each other. And they're coordinated, actually, a lot of the time, ATP phosphates are stabilized by magnesium ions. So that's right there in this active site. We're now going to let the reaction proceed, and the reaction proceeds, and what you get is phosphate gets transferred from the 1,3-BPG, which now becomes 3-PG, right? It lost its phosphate. And now the ADP has become an ATP because the phosphate has now moved from the, metabolite onto the ADP. So we're going to go back, forward, back, forward. Hopefully you can appreciate that simple phosphate transfer reaction. Okay, so what did we just see there? We saw how a pair of enzymes made ATP. They did it by taking the energy to oxidize a carbon with NAD plus in glyceraldehyde 3-phosphate. They couple that energy to an unfavorable phosphorylation, and then they take that unfavorable phosphorylation and they turn it into a favorable phosphorylation of ATP. So there's multi-step process. By coupling these different reactions, enzymes in glycolysis can actually make ATP. What about step 10? Now, you might have said, oh my goodness, that step 6, 7 almost killed me. Don't worry, step 10 is going to be a lot shorter and simpler. So what happens here is we have at the beginning of step 10, actually this is right after step 7, we have 3-PG. This is 3-phosphoglycerate. 3-phosphoglycerate can form 2-phosphoglycerate fairly readily. So I'm just putting this, instead of free energies, I'm putting this in terms of odds. So it's 5-to-1 odds that this reaction goes forward versus backwards. Another way to think about that is if you looked in a test tube with a bunch of these, you would see 5 times more 2-PG than 3-PG, but you'd still see both, right? They're both there, they're both present. Then you have the formation of phosphoenolpyruvate, which has 1 to 5 odds going the other way. And so again, if you put this all into solution, you'd see mostly 2-PG, but then you'd see some 3-PG and phosphoenolpyruvate around. So it's sort of flipping back and forth between these states. This is energetically not very hard to get to, right? Getting a 1 in 5 chance, that's a 20% chance. That's a pretty common thing to have happen just randomly. But then the last step, which is chopping the phosphate off of phosphoenolpyruvate to make pyruvate, is about 1,000,000,000 to 1 forward. And so once you get here, we are going to go to something else. Okay, right. Once you get to here, if this happens, it's a ratchet, right? You've gone there, you're never coming back. And so you can think about this as these molecules can kind of flip back and forth between these states, fine, whatever, and then you get here, ratchet, and now you've released that phosphate. What makes that so favorable? And it turns out this energy just comes from a new bond arrangement. So what I'm doing here is I'm showing not phosphoenolpyruvate, but this is just enolpyruvate up here. So the EP part, enolpyruvate, and this is pyruvate. And we're just going to think about the bond rearrangement that happens independent of the dephosphorylation. So if you look at these molecules, there's basically the top part that I did not circle is the same. The bottom part I circled is different between the two. And then what we can do is we can just count the bonds that are present in those. So for example, there is a 1-hydroxyl bond, which if you look up the bond enthalpy for this, on average, it's 463 kilojoules per mole. You take the CO, right? You've got this carbon-oxygen bond, that's 358 kilojoules per mole. You take the carbon double bond, that's 614 kilojoules per mole, and then you have 2 protons, which I didn't draw, but I'll put them on there so we can see them. We've got those 2 protons there, 414 kilojoules per mole, which means if you add them up, you would guesstimate, just if bond energies indeed add, you'd guesstimate that it's 2,263 kilojoules per mole of favorable bond energy, right? That would be, you would release 2,263 kilojoules per mole if you broke all these bonds. This is a way to think about that. Okay, now we can do the same exercise for pyruvate. Pyruvate has exactly the same number and types of all of the atoms, so we're just rearranging how they're connected to each other. If we do that, we see that we've got one carbon-oxygen double bond, 1 carbon-carbon single bond, and then 3 CH bonds with their associated energies. You add those up, and you get this number that you'd release 2,389 kilojoules per mole if you broke all these bonds. If you take the difference between those two, so where you're going, so your product or your reactants, what that says is, in this simple, if we just can add up bond energies, which isn't strictly true, but just conceptually, if we added them up, this has 126 kilojoules per mole more energy in its bonds. So this is a more favorable configuration of the bonds, going from this enol pyruvate to this pyruvate form. Cool. So you think about it, that was just a simple group adding sort of thing. The actual energy of this reaction is favorable by minus 53.6 kilojoules per mole. So that's the energy you get for the rearrangement of the bonds and the dephosphorylation. But that number is way more negative than the formation of ATP is positive, right? Whoops, wrong direction. So formation of ATP, it gives us 30.5 plus 30.5 kilojoules per mole. You take the difference between those two, and it says, and that is going to be a favorable energy to do this phosphotransfer reaction. This is done inside a pyruvate kinase. We actually only have a structure of it without all the parts, but what we have here is we've got it bound to phosphoryl pyruvate and bound to ATP. That's pyruvate and ATP. So what we basically see here is these are in fact positioned close to one another to do something very similar to what we already saw, where a phosphate can get transferred from the metabolite onto the ADP to make ATP. So by positioning these two together, you can do a very favorable reaction, the enol pyruvate to pyruvate reaction, and then an unfavorable reaction of ADP to ATP, all in one active site. Okay, bunch of details there, but hopefully we can pull out a couple of lessons from these. The first is that glycolysis is actually using intrinsically favorable reactions to drive ADP phosphorylation. At steps 6 and 7, that's the oxidation of glyceraldehyde 3-phosphate to 3-phosphoglycerate using NAD+ as the reducer, as the oxidizing agent. That has more than enough energy to drive the formation of 1,3-bisphosphoglycerate, and then that can dump it off onto ATP. Another way to think about it is this here has minus 50 kilojoules per mole. And skipping that intermediate step, it's only plus 30.5 kilojoules per mole to make an ATP. So you have more than enough energy to drive ATP formation with this. And then in our second position, we're rearranging the enol pyruvate to be a more favorable configuration with pyruvate, and it actually has about similar magnitude energies, right? It was minus 53 kilojoules per mole to do that rearrangement, but then we have a 30.5 kilojoules per mole for ATP. You add those up, you have enough energy to drive production of ATP by doing this chemical rearrangement. This coupling is achieved, we can actually do this coupling by physically linking the reactions in active sites. So in these two different, in the active sites that are involved here, basically the favorable reaction can only occur and is only sped up when coupled to the less favorable reaction, which ultimately leads to the coupled favorable reaction of forming ATP. Okay, so that's what I have on where ATP comes from in glycolysis. Hopefully you found it interesting and helpful. Thanks for watching, and I will see you later.